Okay, so we're here in our lecture folder. I'm going to fire up VENSIM, and the first model I'm going to look at is the model of the Kaiba Plateau and the deer. So I'm going to open that in VENSIM. And let me max out this window so we can focus on it. So this is the model we were just discussing in the lecture before. There's a population stock of deer, and the other stock is the food. Okay, so what I want to do first is sort of walk through the equations that are in the model. So I'm going to fire up this, and if we look at the equation for population, oops, sorry, you can see that the deer have a net growth and a predation rate. The units are deer, and the initial value is 5,000. Okay, for this case, which was about the stable value of the deer before the overshoot started at about right about 1910. Okay, you can see that the deer growth rate here, is a population of deer times the rate coefficient. So it's a first order growth rate driven by a coefficient, and it has units of deer per year, and that coefficient is driven by the food, so it's here, and by a table. And I want to stop and look at these tables. I think there was a little bit of confusion as to how these were used. I want to stop a little bit there today. But the interesting thing is that if you actually go to that rate coefficient, you will see that the equation for it, it's a table 2 as a function of the food per deer. So this is essentially a table tabulated version that shows the relationship between the food per deer and the outcome of this, which is the deer growth rate coefficient. Right? The units of the growth rate coefficient are 1 per year, or basically deer per year per unit deer present at that point of population. Okay, and now I want to show you what this table looks like. And if we look at the table here, let's see. And this is the format that we discussed before. And I'll show you something I didn't show you last time. I think that might have been originating the confusion, but this is essentially what we call a lookup type variable, all right? And the interface of VENSIM allows you to put it in this way, but this is actually not the best way to put it in. If you click here on the Ask Graph window, it will give you a nice little interface that will allow you to put in values of a table. So let me walk you through this interface because I think this will be probably the most likely interface that you will use to produce a table. You have first the inputs and the outputs are given in 2 columns, and the inputs here have are essentially denoted by X. There's an X minimum and X maximum that you can put in. Okay, and in this case, it's 0 and 20. Okay, and there's a Y min and a Y max, which in this case were selected as these 2 values. So those 2, and I'm going to OK out of this for a second, translate into the first, the first piece in this dialog. And this is essentially the range in the table: X min, X max, Y min, Y max. Okay, so I'm going to go back to the graph to show you how the table is introduced. And you can put here in these 2 columns as many points as you want to define this table. But this essentially will give you that for this input, you'll find this output, and so on. Okay, now there's really no limitation as to the number of inputs. I think what you want to keep an eye on is that the values you put in the table are not out of bounds with the values that you define in the range min and max. Okay, that's the only thing you need to look at. And so this will allow you to put 4 points in this case, 5 points, 10 points. You can put some more. And so typically you would have this as a lookup. And then if you do that, this dialog here is automatically generated. So these points here are the points, these 4 points here are the 4 points in that table, okay? Now let me go back to the model, because then, so what this is doing is that if I go back to the deer growth rate coefficient, what deer growth rate coefficient is reading, it's table 2 values where the input is the food per deer, and then the output is the table 2 values, which are values of the deer growth rate coefficient. So what this is telling me is that if I go back to the model, is that the death growth rate coefficient is given by this tabular relationship. So I'm going to click on this again, and I'm going to go directly to this. So these are values of food per deer, okay, 0, 1, 2, 20, and these are values of the growth rate, okay. So essentially for zero growth, although actually the value itself, negative growth would be probably senseless, so this might need to be changed, but it happens to work here in this model okay. And then that drives essentially the deer growth rate coefficient, this table 2 value, okay. So the food per deer is obtained from the food, okay, available as a stock, and the number of deer population. So if you go to food per deer here, you want to look at that equation. It'll be essentially food divided by the deer population, and it's got units of ton, and the food is measured in tons per deer. Okay. So let's get back to it, and now let me go to the food stock. Okay. So the food stock, the equation for that, it's got it's the difference between the food generation rate, that's the plus side, and the food consumption rate, that's the negative side. It's got units of tons, and it's got an initial value of 100,000 tons. Okay, let's take a look at how this how food works. Let's look at the plus side first. The food generation rate has a couple of variables associated with it. There's a variable here that's referred to as the food regeneration time, and the assumption here is that food it actually grows naturally in the plateau, and that's a little bit of what we're discussing. Let's take a look at that variable. And that variable, it's well, first of all, it's given by a table, and I'll go back to this, but essentially I have put a little comment here to define it. So this food regeneration time is dependent on the food capacity and the present food. Okay, so what we're assuming here is that the ratio of the food available divided by the capacity of the Kaiba plateau to produce food, it's a good way of obtaining this food regeneration time using table 3. And we'll look at the table, but essentially when food reaches capacity, the food regeneration time will be a year. So this is like the annual rate at which food can be regenerated. But if this ratio is lower, this will essentially, if you start running out of food, then it will take a longer time for food to get regenerated. Let me go back to the model and let me look at that table 3 here. Okay. So this table 3 again, I'll go back to the graph. It's a lookup variable. Okay. So this is a little bit of what's involved there. Okay. And here, what you have is I'll look at this table backwards. If the ratio between the food available and the capacity or the total food capacity of the reserve is 1, then it takes a year for food to get regenerated. If the available food is about half of the capacity of the reserve, it'll take about a year and a half. And if there's no food available, it takes about 40 years for the reserve to produce again, that level of food available. And again, and this is essentially, when you plot it, it's essentially a ramp that takes place where the horizontal axis is the inputs and the vertical axis is the outputs. And the idea here is very simple: is that you need to tie in you need to provide some way to check that food's not being consumed at too quick a rate. So this time, 1 year, a year and a half, 40 years, gives you an idea of years, here's the units, gives you an idea of how quickly food can get regenerated. So I'm going to go into this. So food gets compared to a food capacity. Okay, I'm going to look at the food capacity here in the equation, and it's 100,000 tons. So that's about the maximum amount of food that the reserve can produce. Okay, and this is sort of like a natural capital concept again, or a carrying capacity concept. It's a very similar variable. So food gets compared to the food capacity. You generate that ratio, and through table 3, you generate that time that it takes for food to get regenerated. And if you look at the food regeneration rate, it's the food capacity minus the food. So this is this difference, okay, divided by that regeneration time. So this gives you an idea how much food can be produced per unit, so tons per unit time year for availability. Okay. Let's look at the negative side, the consumption rate of food. And if you look at that, it's very simple. It's the food consumption per deer times the deer population. And the food consumption per deer, again, it's another lookup table, and we'll look at that. And so there's an explanation here, a little dialogue. Food consumption per deer is dependent on the food capacity and the present food. Okay, so we'll assume that the ratio food divided by food capacity will be a good way to obtain the food consumption per deer using table 4. So when food and food capacity are the same, so when there's plenty of food, we will assume that food consumption per deer is a ton. Okay, so each deer will consume a ton because there's plenty. But if there's a lower ratio, this means that the deer will consume less. Okay, so there's an availability of food that drives the consumption. So the food consumption is tons of food per year per deer, or per deer per year. Okay, so let's take a look at that table 4, and I'm going to go straight to the graph. And this is one of those situations where if you have little information, you can sort of hypothesize a form of this table. And so sometimes when you have no data, but you have intuitively, you can put something that looks like this. So here what you have is and this is the food, the ratio. 1, it's when food available is equal to the food capacity, or you're fully stocked of food, so to speak. This is 40% stocked, 20% stocked, and 0. And then this gives essentially this is 1 ton per year, okay, per deer. If there's a little bit less, deer will eat less, and less, of course, if there's 0, they'll have to eat 0. Okay, and that's pretty much the model. There's an area here that in the reserve, which it's 1 million acres, and that's a characteristic of the Kaiba Plateau that was introduced there, and that helps you define the deer density, which drives again the predation rate. So that's pretty much the model. So you can actually go and run it, and we can just click here on simulate, and it'll get simulated very quickly, and then we can go to graphs and generate the graphs that you saw in the presentation. This is the graph for the deer. Okay, I can go to food and generate the same graph, and I'm going to move it over there. Okay, and so these are graphs we saw in the in the earlier presentation, and you can actually click on any variable here and take a look at it. I encourage you to do it. I think there's one graph that I created. Let's see. There's a graph that I created here. Oh, I did not, but the graph that I created with, you can actually create very quickly, and I'll ask you to play around and do it. You can click here on New, and then you can define a graph with the name and the title, um, and then here you can actually select the variables you want to plot. So if you want to plot together food and deer population, you would select deer. Here you would select food. I could have done it the other way around, just food. And I think I won't put a title just to keep the video short, but you can do that. And then I'll just graph it. I'll just display it, and then you have it right there. See? So you can fool around with VENSIM and create all sorts of nice graphs. Like I said in my earlier presentation, I want you to play around with VENSIM. I want to generate these plots. I want to see plots posted on Facebook. I want to see more activity, which will tell me that you are actually looking at these models in detail. And this is also the best way to learn how to use it, is to really get into it. So I encourage you to start doing this and play around with the model and see what you can understand from these mutual dynamics behaviors. Okay, I'm gonna close out of this, and that's pretty much the explanatory video for the Kaibab population Kaibab deer population in this example. Okay, so we're going to move on to the next case study.